Welcome everybody. So today, Sunday, I am going over solving exponential and logarithmic equations. So this is section 5.4, where you are solving exponential and logarithmic equations, and then it has solving more complicated exponential and logarithmic equations, and then using exponential and logarithmic equations to model and solve real life problems. So I'm going to go start with simple and then complicated. I'm saving the models for my session tomorrow. The session tomorrow is I want to say it's at 6 o'clock. Bring that up on my calendar. Yes, 6 o'clock tomorrow. I'll be going over basically models, which is word problems. And in order to be successful there, you need to be successful with this stuff. So that's why I'm doing this one separately. So I'm going to just start with techniques for solving exponential and logarithmic equations. So we have two different properties that we learned about this week. You have the one-to-one properties, where if you have things with exponents and the bases are the same, then the exponents must also be equal. And it also applies to logs, where if you have the same base on a log, then what you're taking the log of must also be equal. The other thing is the inverse property. So these are two new ways to solve, where if you have a log, you can exponentiate it. Let me write down that word. This is a new process for solving. Exponentiate. And if you have an exponential, you can take the logarithm of both sides. So that's a new way to solve, similar to when we add or subtract on both sides, multiply, divide on both sides. Now you can also exponentiate and take the logarithm. So two new techniques, and you need to do it on both sides when you have an equations. So some strategies for solving these equations is to first rewrite it in a form that allows you to use one of the one-to-one properties. That's the easiest way to solve. So if possible, write it so that you can use a one-to-one property. If you can't, then you would move on to try to use an inverse property. So you would write an exponential equation by taking the logarithm of both sides, and you would take a logarithmic equation by taking the exponent on both sides, essentially. So you're doing the inverse to undo it, because when we're solving equations, if we had like 2 times x, you did the inverse, you divided to get rid of it. So exponents, the inverse is the logarithm, and so on. So I'm starting with the exponents. I'm going to do a problem here with this one where I'm going to show you how you can use both methods to solve. So we're going to do this with the one-to-one property and then using the inverse property. So the one-to-one property means that you need to rewrite this so that they have the same base. So first off, if I have a fraction and then I have an exponent, I can rewrite that 1/2 to 2 to the negative 1 power. That's our rules of exponents. And 32 I can rewrite as 2 to the 5th power. So that I'm just rewriting these as exponents. And then we have our property of exponents, where if you have the power of a power, you multiply those. So on the left, 2 to the negative 1 to the x is, you multiply that. That's negative 1x equals 2 to the 5th. So now we have the same base here, which means the exponents must be equal. So I have negative 1x equals 5. So that is the one-to-one property. I just use that property to get rid of the bases, because the bases are the same, and then I'm left with only the exponents. And then you solve for x. So I'd be dividing both sides by negative 1. And that leaves me x equals negative 5. And there you go. So that's solving using the one-to-one property. And if possible, that's the easiest way to solve. So I recommend trying to do that whenever possible. But if you don't like that, you can use the inverse property all the time. So the way the inverse property works is that you have something with an exponent, and then you take the log or the natural log, whichever you prefer. Both of them works as long as you do the same one on both sides. So I would pick whichever is easiest on your calculator. If you have a graphing calculator, usually the natural log, the LN button, is the one that's there, and there's usually not a button for the log. Now, most people, I think, have the TI-30X, and it has a button for both. It has a log button and an LN button. So let's do the log. So using the inverse property, I have to take the log of both sides. And so I have to physically write that down. Log of 1/2 to the x equals log 32. Then we're going to use the properties of logarithms to take that exponent and put it down in front. So we have x times the log of 1/2 equals the log of 32. Now we're solving for x, so you want to divide both sides by the log of 1/2. And so we have x equals the log of 32 divided by the log of 1/2. And now you need to put those in your calculator. So my calculator, you need to make sure you know how to use your calculator. Some calculators you have to put in the number first, then hit the log button. Mine, you hit log first, then you put in the number. So I'm typing in log 32. Putting my divide button, and then I hit the log button again, and then I'm typing in 1/2. And I have to make sure I close the parentheses. And I get x equals -5. So you don't want to calculate anything with the logs until the very end. So I don't want to take the log of 32 too early, or you're going to have to round, and then once you start rounding, you will get an answer that's not exactly the same. So try not to round until the very end if you need to. So just write things with the logs and then don't do anything in your calculator until the very end. You can see that you get the same answer either way, but as far as which one took less steps and was a little easier to do, I would say that's the one-to-one property. As long as you know your rules of exponents, that's fairly simple. So now example 2. So I've got 2 examples here. The first one, they have the same base, so you want to solve this with the one-to-one property. So we have e to the x squared minus 3 equals e to the x minus 2. So the one-to-one property says that those exponents are equal. So we have x squared minus 3 equals x minus 2. Now here I have something that's quadratic because I have an x squared. So as soon as I see that x squared, that means I'm going to have to put everything on one side to set this equal to 0, because that's the only way we do to solve this. So I need to subtract the x from both sides. And I'm going to add 2 to both sides. And then I need to kind of put everything in line. So I have x squared minus x, and then I have a -3 plus 2, which is -1. And then this equals 0. So now this would be something where you would try to factor or solve with the quadratic formula if possible. So this does not factor. So we'd have to use the quadratic formula. Now I don't have a lot of steps here to show that. So I'm going to write it out and then skip right to the answer and let you fill in the blanks here. So it's -1 plus or minus. So it's b squared, so that's -1 squared minus 4 times a, which is 1, and c, which is -1, all over 2 times -1. 2 times a, sorry, a is positive 1. There's too many 1s here. Actually, let's see. So that's 1 plus 4. Oh, I can do this in my head. This one's actually pretty simple. Okay, so we get 1 plus or minus. Inside the square root, you get 1 plus 5, or 1 plus 4, so you get the square root of 5 all over 2. And I would just leave it like that. Or you can approximate it by finding the decimal values of it, but that would be the exact value. So luckily, because these numbers are small enough, those were easy enough to do in my head all at once, and I can go straight to the answer. So we have 2 answers here, one with the positive and then one with the negative in front of that square root. And that was using the one-to-one property. Most of the time, the one-to-one property, it's designed to come out a little nicer for you just so that you get practice with it. Now the second one here, I have 4e to the x equals 91. We cannot use the one-to-one property here because there's no way to write 91 to a power of e. It won't happen because e is not a whole number. It goes on forever. So it's not easy to make it write things in form of e. So we have to use the inverse property. And to do that, you first have to get your exponent part by itself. So that means I have to get rid of that 4. So I need to divide everything by 4. So I have e to the x equals 91 over 4. So I'm going to leave that as a fraction because we don't want to do any rounding until the very end. Now, if your base is e, then we use the natural log. So the natural log, that is log base e, which we write as ln. That is not a 1, it is an L. Stands for log, logarithm natural. So that is a lowercase l. I see a lot of people writing it as an I or a 1. No, it is an L. So you want to make sure you do the symbol right, because if you don't, then you're writing something completely wrong. So I like to make my L's cursive so that it looks clear. So I make it cursive and do natural log like that. So natural log of e to the x, and then I need to take the natural log of the other side, 91 over 4. So now we have our property of logarithm, which means that x goes down in front. So I have x times the natural log of e equals the natural log of 91 over 4. Now what's special about the natural log of e is that it is equal to 1. That's why I did the natural log, because then that just disappears. If you do the log of e is not equal to 1. So if you see e, use the natural log, and that will save you some work. So we get x equals the natural log of 91 over 4. And then if you want to approximate that, you would put that in your calculator. Make sure you put the 91 over 4 all in parentheses. And we usually round to 4 decimal places. So I have 3.1245, but the number after the 5 is a 6, which means we have to round up. So that is 0.1246. But don't round until the very end. And so, first problem here, we used the one-to-one property. Second problem here, we used the inverse property by taking the inverse of e, which would be the natural log. Now, I'm getting a little more complicated here. There is an example like this first one in the text, but I figured it might be easier if I explain it. So, we have e to the 2x minus 5e to the x plus 6 equals 0. So e to the 2x is the same as e to the x squared because we multiply those exponents. So if you write it that way, you see we have a quadratic equation. Let me switch colors here. Because then we have e to the x squared minus 5e to the x plus 6 equals 0. And it's quadratic in form. So the way I like to solve these is to say let u be equal to the e to the x. And I just do a substitution. This is a method that you would use if you have to go on a calculus, where you have to substitute. But this just makes things a little easier. So instead of seeing e to the x squared, we have u squared and minus 5, and then e to the x, we use u plus 6 equals 0. And doing it that way, now it looks like something familiar. You have a quadratic equation that you can solve. So this is factorable. So I'm going to factor this. This factors to u minus 3 times u minus 2 equals 0. So negative 3 times negative 2 is 6. Negative 3 plus negative 2 is negative 5. And so now I'm going to set each of these equal to 0. So I have u minus 3 equals 0, u minus 2 equals 0, and then I'm going to solve for u. So u is equal to 3, and u is equal to 2. But now we have to go back because our original equation is x. So now everywhere we see u, we have to replace it with e to the x. So e to the x is equal to 3, e to the x is equal to 2. And now I'm going to take the natural log of both sides because I have e's, and I'm going to take the natural log to get rid of those e's. Sort of running out of room here. I had a feeling that I might need more room for these. I had a feeling. So, when you're taking the natural log of something that has an e, essentially those parts just cancel. We saw that because the natural log of e is equal to 1. So on the left I just have x equals the natural log of 3, and x equals the natural log of 2. I'm going to just leave those like that because I don't have any room for trying to simplify those decimal y's. So this is an example where we have something that's quadratic in form, and we did a substitution to make it look nicer, solved with it looking nicer, and then substituted back in, or back substituted is what that's called, where we then replaced our nice variable with what we set it equal to, and then you have to use the inverse property to solve. Now the second one here, so we're solving for e, and we have it in the denominator, so we need to multiply both sides by the denominator of the fraction. So I'm going to be multiplying by 1 plus e to the 2x and 1 plus e to the 2x, because we want to multiply on both sides to get rid of that fraction. So that leaves me on the left side 100, because it cancels out the fraction. And then I have 1 times 1 plus e to the 2x. That just leaves me 1 plus e to the 2x. So I want to subtract 1 from both sides because I want the e part with the exponent by itself. So that gives me 99 equals e to the 2x. So now to get rid of the e, so I can get the 2x out of the exponent, I have to take the natural log because that's the inverse of e. So I'm going to take the natural log of 99, and that is equal to the natural log of e to the 2x. So the natural log of e, that's 1, so that part cancels, and I'm left with 2x on the right. So I have the natural log of 99 equals 2x. So now I'm solving for x. I'm going to divide both sides by 2, and we get the natural log of 99 divided by 2 is equal to x. And you can put that in your calculator if you want to. The natural log of 99, I'd have to close my parentheses and then divide by 2. We get 2.297559925, and we got this. It just keeps going. But it's easy enough to leave it in this form, and you don't have to even touch a calculator. So I prefer not to use a calculator unless I absolutely have to, because I can do all of this without a calculator. I don't have to worry about rounding or anything like that. So these are all the exponential ones. I did, get a bit more difficult. These are the more complicated ones here. These are considered the simple exponential ones, where you can use the one-to-one formula, one-to-one property, or it's just a few steps. This one is also considered a simple exponential equation. So now we're going to move on to logarithms. Now with logarithms, you have to check for extraneous solutions because sometimes you get answers that don't work because of the domain of a logarithm. So I'm going to just put this in the upper corner here. So if we have log x, now this was covered in 5.2, where you talk about the domain. So the domain of log x is from 0 to infinity, because whatever's inside the log has to be greater than 0. If you take the log of 0, you get an error. So we don't include 0, it has to be greater than 0. So we have to consider our domain when we're checking for extraneous solutions. So we have the same problem here. We're going to solve it with both methods, one-to-one property and the inverse property, to show you how they both work. So, and then we'll check for extraneous solutions. So using the one-to-one property, we have the log. It's base 10 because there's no number written there, so it's the same base, which means what's inside the log has to be equal. So 3x plus 4 must equal x minus 10. So that is the one-to-one property that we just used. So now we solve for x. I'm going to subtract x from both sides. I got 2x plus 4 equals negative 10. Then I'm going to subtract 4 from both sides. I got 2x equals negative 14. And then I need to divide both sides by 2. X equals negative 7. So now we need to check to see that that solution actually works. So that's the extraneous solutions. So I'm going to do this in a different color. Let's just do this in green. So inside the log, it has to be greater than 0. So the first log we have here is 3x plus 4. So that needs to be greater than 0. So this is why you had to learn about solving inequalities, because you have to use it once you get here to figure out your domain. So I'm going to solve this for x. So I'm going to start by subtracting 4 on both sides. I got 3x is greater than negative 4. When I divide by 3, I get x needs to be greater than negative 4 over 3. If x equals negative 7, that is not greater than negative 4 over 3. That is not in the domain of 3x plus 4. So that is going to be a problem. But let's double check the other log as well, because of x minus 10. So x minus 10 needs to be greater than 0, which gives us x has to be greater than 10. So our answer of negative 7 is not greater than negative 4/3, and it's not greater than 10. So since it's not in the domain of either one of these, this is an extraneous solution. And you can double check by plugging it back into our equation. So if we do the log of 3 times negative 7 plus 4 equals the log of negative 7 minus 10. Plus 4. So 3 times negative 7 plus 4, that is negative 17. The log of negative 17, if you do this on your calculator, is error, because it says domain error, because it's not in the domain. And so because we have an error, that means this is an extraneous solution, and so we have no solution here. So you need to double check, because sometimes you get things that have no solution. Now, I'm going to solve this using the inverse property as well so that you can see the comparison here. We're still going to get something with no solution. The solution is not going to change, but I'm just going to show you how you could use the inverse property to solve. So we have something with a log. The inverse of log, which is base 10, would be raising it to the power of 10. So we would say 10 to the log of 3x plus 4 equals 10 to the log of x minus 10. So when you have a log base 10 and you 10 to that power, those cancel. So all you are left with are your exponents. 3x plus 4 equals x minus 10. Now you see that is the same thing that we started with when we had a 1-to-1 property. So in this case, using the inverse property gets us to the same point as the 1-to-1 property. It's just essentially one extra step. I will show you ones where that doesn't happen. This is just examples showing how the inverse property works. Ideally, you want to use the 1-to-1 property, and then you have to check to make sure your stuff is in the domain. That's why we learned about domain. That's why we learned about linear inequalities, because you need that stuff here. And I have a note on all of these. Don't forget to check for extraneous solutions. Always have, because that's the most common thing. People forget to check for those. And I forget all the time myself, because it's like most of the time the book is designed to give you actual solutions. Rarely is the book designed to give you extraneous solutions, but real life gets you extraneous solutions. So that's why we need to remember to check. So I'm going to start with this example on the left. So we have 2.1 equals the natural log of 6x. Because we don't have a second natural log in there, we cannot use the one-to-one property. So we have to solve by doing inverses. So the inverse of a natural log is having the power to e, because e and natural log are inverses. So I'm going to have e, let me try writing that again, e to the 2.1 equals e to the natural log of 6x. Now e and natural log cancel, so that disappears and we are left with 6x on the right. So I have e to the 2.1 equals 6x. So now I need to solve for x. So I'm going to divide both sides by 6. So I have e to the 2.1 over 6 equals x. Now we need to check for extraneous solutions. So just like the log, the natural log, your whatever's inside needs to be greater than 0. So I'm going to do this in a different color. So we have 6x needs to be greater than 0, which means that x, if you divide both sides by 6, still has to be greater than 0. E to the 2.1 over 6, that is positive, because e will always get us positives. And you can verify that on your calculator. You can actually find the decimal, e to 2.1, divide by 6. We can find the decimal approximation there. That is about 1.361. So that's positive. So that's greater than 0. So we don't have any extraneous solutions. This is our solution. E to the 2.1 over 6, or if you prefer, you can round it. So now let's take a look at the second example. Again, I only have one natural log here, so I need to use the inverse property, but that, in order to use it, I have to first get that natural log by itself. So I need to first subtract 3 from both sides, because I need to isolate the natural log. So that gives me 8 natural log of x equals 4. So now I want to isolate the natural log. I have 8 times that, so I want to divide both sides by 8. So the natural log of x equals 4 over 8 is 1/2. So now to get rid of the natural log, I have to do e. So I have e to the natural log of x equals e to the 1/2. So I'm going to cross out my e in the natural log. Those cancel. And we're left with x equals e to the 1/2. And I know this is not an extraneous solution because according to our domain of the natural log of x, x has to be greater than 0. And e to the 1/2 is greater than 0. So I've solved and I have a solution. There were no extraneous solutions for these two. So these are simple logarithmic equations to solve. let's take a look at complicated ones. And these we have to use the properties of logarithms to sort of make it easier for us. So on the one on the left, we have natural log of x minus the natural x plus 1 equals 2. So if it was equal to 0, we can just put these on opposite sides and use the 1-to-1 property. But because it's equal to 2, we can't. So we need to use the property of logs where you have the subtraction and you can combine that into division. So this is why we have to learn the properties of logs. So this is the natural log, and I have to put these in parentheses. So natural log of x, that's the top. What's in after the subtraction, that goes in the bottom, so that's x plus 1 equals 2. So we have the natural log of x over x plus 1 equals 2. And just for our domain purposes, we have to have x greater than 0, and then x plus 1 greater than 0, which means x greater than -1. But the bigger one, so x greater than 0. So x has to be bigger than 0 once we're done solving. So to get rid of the natural log, I need to raise e to both sides. Now I usually do this by just writing in my e there so that I don't have to rewrite the whole thing. If you're typing it, you can't exactly do that. But when I'm doing it on paper, that's what I will do. I will write the e underneath it so that you can see that I'm doing e to that power on both sides. So on the left, the e and the natural log cancel, and I'm left with x over x plus 1. And on the right, I have e to the second power. So now I need to get rid of that. I have an x in the top and the bottom of my fraction here. I need to eliminate fractions. And so I'm going to multiply both sides by the denominator to get rid of the fractions. I'm going to multiply both sides by x plus 1. So that leaves me with x on the left because the denominator cancels, and it's equal to e to the 2, and then I need to distribute here because I need to get my x's all on one side. So I'm going to multiply that through the parentheses. So that's going to be e squared x plus e squared. So now I need everything with x to be on one side because I need to factor the x out. This is a little trick. We've done this before. I can't remember. Oh, I know we did this trick before. I can't remember where it was that I showed you guys this trick. It might have been in week 3 when we were just solving these types of things. But I'm going to subtract the e squared x on both sides because I need the x's on the same side in order to solve this. So I have x minus e squared x equals e squared. And I'm going to factor that x out so that I can solve for x. So I have x, and then in parentheses, 1 minus e squared. And then we solve for x by dividing on both sides. So I'm sort of running out of room here. X equals, I'm going to actually move this slightly over. X equals e squared over 1 minus e squared. So now we need to make sure that is greater than 0. So I'm going to just put this in my calculator, and you want to be very careful how you put it in. So e squared, I'm putting that in, and then I'm hitting divide, and then I need to have parentheses for the denominator. So I have a parenthesis, 1 minus e squared, close that parenthesis, close the second parenthesis, and hit enter. This gives me a negative. So that is an extraneous solution. I got a negative when you solve this. When you get that, put that on your calculator, you get negative 1.1565. Negative 1.1565. So because that's negative and that is not in our domain, that is extraneous, so we have no solution. So again, it looks like you have a solution, but you need to check, and it's a lot easier to check when you make it a decimal form. So now let's take a look at my second problem here. Next time I go through these, I'm probably going to put these all in different slides instead of putting them two to a slide because there's clearly not enough room. Okay, so this is the same sort of thing before, except now we have base 4. So log base 4, that's totally fine. But we do need to use the rule where you're subtracting logs that it turns into a fraction. So I have the log of x over x minus 1 equals 1/2. So all I did, and it's log base 4, so I have to remember to put that 4 there. So I have log base 4 of x over x minus 1 equals 1/2. So the base is 4, so in this case we want to raise everything to the power of 4. So I'm going to write that in green here. So I'm going to take 4 with the log as the exponent and then 4 to the 1/2. So we're going to use 4 as our base of that exponent when we exponentiate. And that 4 and the log base 4 will cancel, so we're left with x over x minus 1 equals 4 to the 1/2 power. Now the 1/2 power is the square root of 4. Square root of 4 is 2, so that's just equaling 2. So just like what we did on the previous one, we need to multiply both sides by the denominator. So I'm going to multiply by x minus 1 on both sides. So the denominators cancel. I have x equals, and then I'm going to distribute 2x minus 2. So now I need to subtract 2x from both sides. So 1 minus 2, that's negative 1. So I have negative 1x equals negative 2. Divide both sides by negative 1. I get x equals 2. So this is in our domain, because our domain, if we look at our logs here, log base 4 of x, x has to be greater than 0. And for x minus 1, which has to be 0, has to be greater than 0, x has to be greater than 1. 2 is greater than 0 and 1, so that's in our domain. So we have a solution for this second problem here. So that's it. So I didn't stop for any questions because nobody's actually watching this one live today. If you have questions at any point during this video, you can send me an email or give me a call, or you can send me a Hangout chat, and I'd be happy to help you out, show more steps if I need to, explain something further, whatever you need. So I hope this is helpful for you to understand how to solve logs. Hopefully you've seen how some of the things we did back in week 3 have popped up and you need to use them again. Definitely if you're going on to calculus, you're going to need this. If you go into pre-calculus, we do some stuff with this as well. So this is going to be helpful for those who have to go on to more math. And if you do anything with electronics, a lot of stuff with electronics involves imaginary numbers and converting imaginary numbers into things with the power of e. So it'll be e to something. And so those who are going into engineering, this will pop up as well. So again, if you have any questions, of course, please reach out. And I hope you have a great day. And I gotta figure out how to get to where I can close this and stop the recording. Okay, I will talk to you guys later.